All right, so for problem 23, section 2.1, we'll call this classwork 1. The maximum data point in that data set is 283, while the minimum data point is 206. So using 6 classes, we can determine an appropriate width for each class. If we take the range of our data set and divide it by the number of classes we're going to use, which is 6. So the range is going to be 283 minus 206 divided by 6. And I believe that gives us like 12 point something as a decimal. But I'm going to round it up to the next whole number. And I'm going to call our width a nice 13. All right, so we're going to let each class take on a width of 13. And I would like you to start the first class off at 206. Now, so we'll start the first class off at 206. Okay. And then we can just use class limits here. We don't have to use class boundaries. I'll be happy with class limits. So this is the lower class limit of our first class. And then we're going to have a frequency column, right, for each class. All right, so let me put this down a little bit lower here. So we're going to make a frequency distribution table. So we're going to have our class column, which is going to start at 206. And we're going to have our frequency column. Okay. So the first class is going to go from 206. Now the lower limit of the second class is going to be 206 plus 13, which is going to be 219. That will ensure that our classes have a width of 13. So just keep counting off by 13. So 219 plus 13 is going to give us 232, I believe. Is that correct?
Yep.
232. And 232 plus 13 is going to be 245. Remember, there's 6 classes. So 1, 2, 3, 4. 245 plus 13 is going to give us 258. That's 5 classes. And our last class is the lower limit of the last class is going to be 258 plus 13, which 271, is that correct? I believe. Let's see. 271. All right. Now the upper classes, 206 is going to go up to, I'm going to take 206 up to 219, and then 232. Now, this is the thing. Because we're not using class boundaries here, we're using class limits to represent our classes. Okay, so these classes all have a width of 13, correct? Remember, there cannot be any overlap between classes. They must have a width of 13, and they must be collectively exhaustive in the sense that they have to allow for every data point to fall in one class. So you cannot omit any data. Notice our largest observation in this data set was 283, and it will fit nicely into this last class.
This meeting is being recorded.
And the last, the minimum value in this data, and that'll fall in here. Okay. All right. Now, so I want you to go from here. Now, the rule we have to establish, so we're on the same page as the class, is that if we have any data observation that is less than, let's say, 219, less than 219, less than or equal to 219.4, we will include it in class number 1. All right. But you know what, ladies and gentlemen, I don't think we're going to have to worry about any decimals. Do you agree? But you would want to establish a rule if you did have a decimal conflict here. So like if you get like a data point that's 219 or 232 or 245 or 258 or 271, you have to establish a rule. And we need to, not only establish a rule, but we need to apply it faithfully and to every class. So what do you want that rule to be? And it really doesn't matter to me. Like if we have a data point that's like 219, all right. So if X is equal to 219, let's say we have an observation in our data set that is 219, the rule we'll use as a class is that we will only put it in the first class, not the second class. So like if I got 245, that's going to go in this class, not this class. If I got 258, it's going to go in this class, not this class. If I got a data point that's 271, it's going to go in this class, not this class. Okay, so that'll be the rule we use. And now I want you to finish this frequency distribution table. I'll let you do that. And we'll call this class work number 1. I pretty much got you almost half of the way there by establishing the classes, et cetera, et cetera. Okay, so go ahead and finish this up. We'll call this class work number 1.
Will you want the cumulative frequency as well, or just the frequency?
We're just doing a frequency distribution here. So we'll just do that for now, okay?
Okay, thank you.
Okay, are we ready to look at this frequency distribution table? All right, check it out. All right, let's see if we got it correct. Now, we had a couple of observations that were 271 and 232, but remember the rule I established for our class here in this thing. The rule I established was that if we have a 231, excuse me, a 232, we're going to include it in the first class here, not the second class. So I threw it into this class. 271, we don't include it in this class. We only include the 271s in this class. That was the rule we established. Okay. All right, there it is, ladies and gentlemen. Make sure they do total up to 32. If they don't add up to 32, the size of your data set, that means you lost some data points, and that's a bad thing. Okay. But that's what I got. Did anybody get this?
Yep.
Okay, that's called a frequency distribution table. Now, here's what I want you to do. Right below this, I want you to, because these were class what limits, correct? Right below this, I want you to do the same problem over again, but I want you to use class boundaries. So all you got to do, pretty simple thing, is just convert all of these into class boundaries, all these classes. The frequencies will be the same. We're not going to change the frequencies, okay? All right, so go ahead and do that. This is still part of classwork number 1. Convert all of these into class boundaries. Frequencies will remain the same. All right, go ahead and do that. Class boundaries now.
I have a question.
Go ahead.
How come like you see how like you have it where it's like 206 and then it goes to 19? How
Hmm.
come it's not like 206 and then it goes to 218? Because like on some of them, it's like if you go to page 44 in the book,
Remember,
like
the width is computed by taking the difference between successive lower limits or successive upper limits. Or if you have class boundaries, you take the difference between the class boundaries here. So these better all be separated by 13, correct? These had all be, these got to be separated by 13. All right, isn't that true? That's how we determine the width. We don't determine the width with class limits by taking the difference between this and this. Okay, not with class limits. All right.
okay.
So these have to be 13 apart. These have to be 13 apart. All right. And I believe they are. What's that?
So for boundaries, then you're just basically you're doing like how she said. So that's the difference between limits and boundaries. So it would be 206 to 219, and then your next one would be
No. Remember what boundaries were? Boundaries are always a half subtracted off or a half what added on. So what's going to be the lower boundary here? 205.5. And the upper boundary is going to be 219.5. Remember, class boundaries are always a half. That's going to be your class boundaries for the first class, 205.5 to 219.5. And then you got to do the other ones same way. All right, go ahead and do that. Class boundaries. All right. All right, ladies, the class boundaries are not going to be correct with this here. Let's just go with the class limits here. The class boundaries are going to be off because I should have went to 206 to 218 and then 219 to 231. Okay. So the class boundaries are not going to be correct here. But let's just go with the class limits. What I want you to do now is just using class limits here. Let's see if we can make a frequency histogram for this. Okay. And I'll show you the correction as to what we should have done with this for class boundaries here. But I would like you to make a frequency histogram. And a frequency histogram, of course, has a vertical and horizontal axis. The vertical axis is labeled the frequency axis, and the horizontal axis is labeled the class. These are your classes down here, class axis here. Okay, so what we'll do is we can have a break in the graph from 0 up to, and we can start off at 206, and we can run this right into 219. And then 219, we can go up to 232. And 232, we can go up to 245. And 245, we can go up to 258. 258 to 271. And then to 284. Okay. All right. So that's how you can lay these off with your class limits here. All right. And this is your first class, second class, third class, etc. All right. So notice your frequencies. The largest frequency is 8. So you need to scale your y-axis appropriately so that you can fit in the heights everywhere. So to build a frequency histogram, we would probably, you can lay your tick marks off by 1 here. 1, 2, 3, 4, 5, 6, 7, 8. Space them 1 unit apart. Okay. And then your first class has a frequency of 7. All right. So you go 7 high on this one. That's your first class. Second class goes 6 high. Third class occurs with frequency of 3. Fourth class occurs with frequency of 6. And the last class, next to the last class occurs with frequency 8. So we're up here. And the last class occurs with frequency of 2. So we're down here. All right. So there you go. It appears that this class is close to being what, bimodal. All right, and actually a U-shaped type graph. Okay. All right, so that'd be a frequency histogram there. All right. So that is a frequency histogram. Okay. Now, what I want you to do is I want you to take this same table here with these classes that we have here, and I would like you to add an extra column here, which we will call the cumulative frequency classes. Okay, so we're going to make a cumulative frequency distribution table from this one. We're going to add on to this. And what kind of classes would we have for our cumulative frequency? Well, we'll have a class here that goes all the way up to 206. So up to 206. And then we'll have a class that goes up to what? 219. Then up to 232. Up to 245. Up to 258. Up to 271. And up to 284. All right. So please add on to your table these extra cumulative frequency classes here. We'll call them the cumulative classes. And now I want you to populate the cumulative frequency column, okay? This is all part of exercise 1 or classwork 1. So I want you to fill in these cumulative frequencies then, okay? Based on how we established the cumulative frequency classes. So go ahead and do that. So we've converted our frequency distribution table into a cumulative frequency distribution table. That's what we've accomplished here, okay? So go ahead and populate the cumulative frequency column. All right, so these cumulative frequencies have to accumulate. So up to 206 would be 0. Up to 219 means you cut through the first class. That would be 7 observations. Up to 232 means you cut through the first 2 classes, which means 7 plus 6 more observations is 13. Up through 245 means you cut through the first 3 classes. So 13 plus 3 is 16 of the observations accounted for. Up to 258, you cut through the first 4 classes. So you add 6 more to 16, you get 22. Up through 271, you've cut through the first 5 classes, which means you add 8 more to the 22, and you got 30. And up through 284 means we've cut through all the classes. We've got to add 2 more to 30, and we get 32. This would be your cumulative frequency distribution table right here. Okay. That makes sense, sir?
Yes.
Just make sure your last class with a cumulative frequency distribution table, okay, the cumulative frequency adds up to the size of your data set. If it doesn't, that means you got a mistake. You missed some data in here. All right. This would be the appropriate way. You don't have to write this down, but this would be the appropriate way to have established the class limits versus the class boundaries. And now this ensures that all of our classes have a width of 13, whether you do the difference between adjacent lower limits or the difference between adjacent upper limits or the difference between class boundaries. You'll have a width in each case of 13. Okay. So that's the proper way for this problem to go from class limits to class boundaries. Alrighty. You would just have to have a rule, like if you had a data point that was like 218.4, you'd have to establish a rule. Do you include it, throw it into this class or this class? Or if you had a data point that was 218.5, you have to establish a rule. Would you include it only in this class, or would you throw it in this class? But whatever rule you establish for like 218.5, you would have to be consistent in establishing the same rule for the rest of the classes and the rest of your observations. That's the key, is consistency when you establish a rule. Okay. All right. Now, so what we've accomplished so far in classwork number 1 is we've constructed a frequency distribution table. All right. And we'll go with these class limits here, although we should have gone with these here. All right. And ladies and gentlemen, we've also constructed a cumulative frequency distribution table here. Okay. So what I want you to do now is, using your cumulative frequency distribution table, I would like you to build a cumulative frequency graph called an ogive graph. So let's see if we can build an ogive graph from our cumulative frequency distribution table. All right. So this is still part of classwork 1. See if you can build an ogive graph now. Okay, so an ogive diagram is going to look like this. Notice you got to start off at 206 at 0. And by the time you cut through the first class, you have 7 observations, et cetera, et cetera. Okay, so that would be an example of an ogive diagram for this data set. Alrighty, and it's nice to label these points with the cumulative frequencies. It makes it just so much more readable and much more useful. All right, we got that there. Okay, now the next thing I want you to do, ladies and gentlemen, is I want you to go back to the frequency distribution table right here. And I want you to add another column in, which is going to be called the midpoint column. So you're going to have to find the midpoint of each of these classes, coupled with the frequencies, and then you can build what's called a frequency polygon graph. Okay, so that's the next thing I want you to do is build a frequency polygon graph. Just take your frequency distribution table and add another column in here, call it the midpoint column. And then you can, from that table, then make your frequency polygon line graph. All right, so go ahead and do that. A frequency polygon graph. Still part of classwork 1. All right, so there's the alteration of a frequency distribution table to allow for a class midpoint column. These are the midpoints of each of these classes. They're found by just adding up the endpoints, dividing by 2. Frequencies remain the same. We can then go to our frequency polygon graph. And this would be just a graph. It's a line plot. Notice on the horizontal axis, I have the class midpoints. No class limits or no class boundaries, just class midpoints. We got the frequency axis there. Okay. All right. So we'll call that all classwork number 1. We're done constructing various graphs. We constructed a frequency histogram from the frequency distribution. We constructed an ogive graph from the cumulative frequency distribution table. And we constructed a frequency polygon from the midpoint frequency distribution table. Okay. All right, so we'll call that classwork number 1. All right. All right, so that's classwork number 1. Now, section 2.3. All right, data set number 16 here. 50 off-campus students were asked how long it takes them to get to school. The times and minutes are shown. Construct a dot plot to basically organize this data. So I want you to build a dot plot. Remember, a dot plot just makes use of one horizontal axis. You're gonna have to scale your axis according to, the range of this data. So what you might want to do is just type this data into a list and sort it. You'll be able to compute the range, and then you'll be able to lay off an appropriate scale on your horizontal axis. And then you basically start locating where each of these data points lie and just put a dot. If you have repeated data points, of course, you just stack the dots. This is called a dot plot. Let's see if we can do a dot plot with this data first, a dot plot. So I would recommend you throw this data into your calculator and sort the data, ladies. I'm just going to make your life a million times easier. First, sort the data.
Is this classwork number 2?
Yes, this will be classwork number 2.
Okay, and it's number 16, right?
Yep. Number 16. Yep. That's the data set we're using. I want you to build a dot plot for this data set. there's my dot plot. I laid my scale off from 11 to 36. If you had a larger range than this, and you'd have to probably go to a more coarse scale, like spacer tick marks by 2 units apart, or maybe 5 units apart, etc. But this was doable, 11 to 36, and basically you just determine how many occurrences, depending upon how many dots you stack up as to how frequently each number occurs, okay, or each observation occurs. That's called a dot plot. As we're finding out, ladies and gentlemen, statistical graphs are tedious. They take a lot of time. We burn a ton of time here. And so we're going to move on now. So that will be classwork number 2. If you can get that stuff to me by midnight tonight, that'll be great. Okay. All right. We're going to wrap it up today by looking at, or start to look at, measures of central tendency. And these statistics that we're going to learn how to compute are going to give us a measure as to the center of the data set. Okay.
I did have a quick question on this classwork. I didn't get a 36 in the data set. I think you mislabeled a 26 as 36.
I also didn't get a 36. I was going to ask
Okay.
about it.
Let me see.
And you're also, I have an extra 26.
I may have done that. Yeah. All right. I'll have to double check that there. All right. So we're going to move on, ladies and gentlemen. Now, I did have a chance to look at Alex and how they're going to have you build these various graphs. And they do a pretty good job. I mean, it's pretty user friendly. It doesn't look like you have to do this like purely from scratch, these graphs. It basically, Alex kind of sets it up a little bit for you and then kind of prompts you just to enter in numbers in appropriate places and stuff like that. So it's really not that bad. So I did open up that homework last night, so you might want to get started on it as soon as possible. Okay. On sections 2.1 through 2.3. All right. Okay, so let's close this out here and let's get into section 3.1. All right. Okay, we're going to learn how to compute what are called measures of central tendency, such as the mean, median, mode, and mid-range of a data set. We're also going to show ourselves how the mean and median do differ as far as their ability to locate the center of data, especially when your data set is plagued with what are called outliers. Okay. All right. First of all, ladies and gentlemen, we need to draw a distinction between any quantity computed from a population versus a sample. Any quantity computed from a population is called a parameter, and any quantity computed from a sample is called a statistic. Okay. So if you compute the mean of a population, it's called a parameter. If you compute the mean of a sample, it's called a statistic. All right. All right. Now, measures of central tendency are going to be numeric values that give us a measure of the center of the data set. And we're going to look at what's called the mean or the average of a data set, the median, the mode, and the mid-range. Okay. Normally, the mean and median are used the most. The mode is used a little bit. The mid-range is not really used very often, in all honesty. Okay. All right, so how do you find the mean or the arithmetic average, or sometimes we call it an unweighted average of a set of data? Well, the sample mean, first of all, is a statistic, and it's denoted symbolically with X with a bar above it. So X bar is the universal symbol used in all stats books to represent the mean of a sample, okay? And to compute the mean of a sample is pretty simple. All you do is you add up all your data values in your sample, and then you divide by the total number that you added up. To put this more compactly, we would use what's called summation notation. This sideways looking M here is called uppercase sigma. It comes from the Greek alphabet. It means you're going to be adding things up. So whenever you see that symbol, that means you're going to be summing things up. So you sum all your observations up in your data set and divide by the number you added up. Ladies and gentlemen, you have the mean or the average of that sample, denoted as X bar. Notice the size of a sample is lowercase n. Population mean represented in all stats books I've ever seen by this lowercase character from the Greek alphabet called mu. That's its name. It kind of looks like a U, but it's a U with like a little tail on it. Mu is universally used to represent the mean of a population. And since it's computed from a population, we would call it a parameter. Okay, so a population mean, like a sample mean, is computed by adding all the observations in the population together and dividing by the population size. Uppercase N represents the size of a population. So we have to, become familiar with the symbolism that's used in statistics, as there's quite a bit of that. All right. Here is a small sample that represents system-wide sales in millions for U.S. franchises of a donut store over a 5-year period. These are the sales in millions of dollars. We want to compute the sample average, or the sample, or the unweighted arithmetic mean of this sample. And to do so, we basically just add all of our data values together and divide by 5. And we will get a sample average, X bar as being 264.2. So that we would say the mean sales per year is 264.2 million. All right. Now, notice this data is ordered from left to right. Stop my cursor when I have located the mean of this data set, X bar. Approximately when I locate the mean, tell me where to stop my cursor. Here we go.
Stop.
Okay.
Here.
Somewhere right about in there. Do you agree? All right. So we can see that this arithmetic mean for this sample does a fair job in locating the physical center of the data set. Okay. Does a decent job. All right. Any questions about how to compute the mean of a sample? All right, now this mean for the sample was a mean of what's called unweighted data, in the sense that every data point was weighted with a weight of 1. Okay, so we call this an unweighted mean. But, ladies and gentlemen, oftentimes we have to deal with group data, okay, in the form of some sort of a frequency distribution table, whether they use class boundaries or limits. All right, and how would you compute the mean of group data? Okay, well, in order to do so, you're going to have to add an extra column to your table called the midpoint, the class midpoint column. And the class midpoints are found by adding up your endpoints, your class limit endpoints, or your class boundary endpoints, and dividing by 2. Once you generate a midpoint column, you multiply your frequency times your midpoint to generate this last column. So 234 came into existence by taking 13 times 18. 138 came into existence by multiplying 6 by 23. You see, the midpoint represents the class. The frequencies are the weights of each of these classes. The frequencies are the weights. And because the frequencies are not the same, you can see that these classes are weighted differently. That's why we call this a weighted average, or a weighted mean of group data. All right, so we're going to take this last column and add together the products of the frequency and the midpoints. Then we're going to divide that sum by the sum of our frequencies, okay, which must add up to the number of data points in your data set. When you do this division, you generate what's called the arithmetic mean, or the average of this grouped data set, 22.2 million. And you can see that 22.2 million would lie somewhere like right in between here in this second class here. So we would call that the average, or the mean, of this group data set here. Okay. All right, the median is literally the middle data point of your data set, whether it actually is in a data set or not in the data set. It is the middle value, the physical middle value of your data set. Ladies and gentlemen, in order to compute the median of a data set, step number 1 is you have to sort your data. If you don't order your data, there is no way you're going to find the median. Okay, so here's an example. They give us a small data set here, which is originally unordered. The first thing we need to do is order the data set, or sort it, and they've done so from left to right, smallest to largest. All right, and now to find the median value is always going to be, okay, the actual middle data value of your data set when you have an odd number of observations in your data set. If you have an even number of data points in your data set, the median will be the average of the middle two values of your data set. We can see this small data set has an average, a size of 5 observations. And so the median literally would be 57, which is the physical middle data value of the data set, because we have 2 observations to the left of 57 and 2 to the right. Okay. If we have this other data set, which now has an even number of data points in it, the median is going to be, and notice this data set has been sorted or ordered, which is a requirement. The median here is going to be the average of the middle 2 data values, which is the average of 128 and 135. So those are the 2 middle values of your data set, because to the left of those 2 middle values are 2 observations, and to the right there's 2 observations. That's why we call those the middle 2 data values. When you find the average of the middle 2, you crank out the median of this data set, which is 131.5. Now these data sets are small. What happens if your data sets are really large? Well, thankfully, we normally turn it over to a computer system. But in general, this is what you want to keep in mind. Whether your data set has an odd or even number of data points in it, you want to find the rank of your median value. And the rank of your median value is found by taking the number of observations in your data set, adding 1 to that, and then dividing by 2. This is the rank of your median value. For instance, this first data set has 5 observations in it. So the rank of our median value is going to be 5 plus 1, which is 6 divided by 2 is 3. So the median value is going to have rank 3. So here's rank number 1. Wrong. It's got to be the sorted data. Here's rank number 1. There's rank number 2. And there's rank number 3. That's why this is the median value, because it has rank 3. Okay. What would be the rank of the median value of this data set that has 6 observations in it? Well, the rank is going to be 6 plus 1, which is 7, and 7 divided by 2 is 3.5. So the rank of the median value of this second data set is going to be rank 3.5. Here's rank 1 of the sorted data set, rank 2. Here's rank 3, and here's rank 4. Rank 3.5 falls dead center between 3 and 4, ranks 3 and 4. And for that reason, your median is literally the middle value of 128 and 135. For that reason, that's why we're taking the average of the 2 middle values to find the median value. So this always gives you the rank of the median value of a data set, where n is the number of data points in the data set. Okay. For small data sets, you don't really have to do this rank thing. You just got to remember, for like an odd numbered data set, the median is literally the physical middle data value. And for an even numbered data set, even number of observations, it's the average of the middle 2. Okay, that's how you find the median. And the median always will literally physically be the middle of your data set. The mode is a third measure of central tendency. It is the most frequently occurring data point or data points in your data set. That's what a mode is. Some data sets only have 1 mode, in which case we call it unimodal. Some data sets have 2 modes, in which case we call it bimodal. Any data set that possesses more than 2 modes, we call it multimodal. Okay. Now, it is not correct to say that the mode is 0. If no data values occur more than once, in that case, we would say one of 2 things. Like if I had a data set that had observations of 1, 2, 3, 4, and 5 in it, you can see that every data point occurs with equal frequency of 1 time. Now, I've seen different textbooks call the mode of such a data set 2 different things. So there's 2 schools of thought here, and I would have to accept either answer. Some textbooks say that there's no mode for this data set. It doesn't say 0 modes, it says no mode. But I've seen other stats books say that every one of these data points is a mode, because technically speaking, there's a tie of occurrence between all of them. They all occur with equal frequency of 1. So I've seen some stats books say that there's 5 modes in this data set. but other textbooks say that there would be no mode. So, I mean, I don't think you have to worry about this, but if I was grading a problem like that, I would have to accept either one of those answers, okay? Either you say no mode or 5 modes. When would we say the mode is 0 in a data set, or 0 is the mode? Well,
Never.
well, we could say that if we had a data set like this. Let's see. You agree, ladies and gentlemen, 0 occurs most frequently here?
Oh, yeah.
So
Yes.
0 would be the mode for this data set. Is that clear? Okay, that'd be an example where 0 would be the mode. All right. Now, what is the mode of group data? Like if it's grouped into a frequency distribution table or like a histogram? Well, the mode is going to be equal to the class with the largest frequency, or it's going to be the largest frequency of any class in the frequency distribution. So the mode is the most frequently occurring class value. All right. Here's an example of a data set. They sorted it, and the most frequently occurring data point in a data set is 19, so that would be the mode. And that would be a unimodal data set since it only has one mode. Here's another data set here. Let's see, is it sorted? It looks like it's sorted. And it appears that 61 occurs with frequency of 4 times, and so does 68. So there would be 2 modes in this data set, 61 and 68. That's a bimodal data set. Okay. This data set they're indicating has no mode. So apparently the author in this textbook says no mode. Okay, but I have seen some stats books that would say that all of these data points are a mode. But I think the more general or the more opted for consensus on this situation is to say it has no mode. Okay. All right, the mid-range. The mid-range value is computed by basically adding your smallest data point to the maximum data point in the data set and dividing by 2. So the mid-range is the average of the minimum and the maximum data observations in your data set. That's all there is to the mid-range. And so the mid-range of this data set would be 54 plus 79 divided by 2, or 66.5. The median of this data set is 63. And the average of this data set, they went ahead and computed that. And they determined, they determined that the average is 64 there. Okay. You can see that all of these measures of central tendency are fairly comparable to each other. All right. The median is literally the middle value of the data set, though, when sorted. The mean does a fairly good job in computing the middle of the data. And the mid-range is a little bit further off, but nonetheless does a decent job. Which one of these statistics is most susceptible to what are called outliers in a data set? An outlier is a data point that is uncharacteristically much larger or much smaller than all the other data points in the data set. And when we get into measures of variation, ladies and gentlemen, we'll show you an actual test you can subject a data point to determine if it actually qualifies as being an outlier. All right. But if you take your eyes and scan through these data points here, it doesn't really look like there are any outliers in this data set. It looks like all the data points are pretty much comparable as far as relative sizes are concerned. Now, if we had a data point in this data set that was like 5,000, do you agree there's a pretty good bet that this would be called a what? An outlier in a data set? Doesn't look like it fits. Do you agree? We'd probably call this an outlier. All right. And I have a question for you. Which of these 3 measures of central tendency do you think would be most susceptible to outliers? In other words, would be most affected by outliers? Anybody want to take a guess?
The mid-range?
Okay, you're right. The mid-range would be adversely affected big time because the mid-range is totally oblivious to all of your data points except 2, the minimum and the maximum. That's it. So it looks like the mid-range value here would be the average of 5,054. Do you agree? And what would be the average of 5,054? it would be 2,527. Now, does it look like 2,527 is a good measure of the middle of this data set? Not even close. So when your data set has outliers in it, ladies and gentlemen, we should not be using the mid-range for a measure of central tendency. Which of the remaining two would also be susceptible to outliers? Anybody want to take a guess? Median or mean? Which of the two remaining statistics would also be affected rather largely by outliers? Median or mean?
The mean.
The
The
mean.
mean. You are correct, the mean. The mean, although it is blessed with taking into account every data value in a data set in its computation, also unfortunately becomes susceptible to outlier existence in your data set. So the mean also becomes a poor measure of central tendency if you have an outlier in it. Because the reason would be, ladies and gentlemen, if I have 5,000 in my data set, you'd have to add 5,000. And then you divide this by what? 21. Do you agree? So what would be the mean if we had 5,000 in the data set? Well, it would be 1280 plus 5,000, which is 6,280 divided by what? 21. And that would give us a measure of central tendency for the mean as being 299. 299 does a lousy job along with the mid-range value in determining or indicating the middle of this data. So when your data set is plagued with outliers, you should not be using the mid-range value or the mean value for the middle of the data set. You should be using the median. The median, regardless of outliers, still will always give you the middle value of your data set because it only is based on ranks, okay? All right. So you should not be using the mid-range or the mean when your data set has outliers in it. All right, how about a weighted mean? Well, we already kind of seen that in a way with group data, but it also is used to compute the mean of other group data sets. For instance, an example comes to mind in computing your grade point average, ladies and gentlemen. In order to compute your grade point average, you would take the weights, which would be the credit hours of the class, and multiply by the GPA attained. Add up all those products and you divide by the sum of the credit hours. And that would give you your GPA, your grade point average for that particular term there. So these W's are weights and the X's are data point observations. Assuming that W1, W2, the W sub n are not all the same weights, we would be computing what's called a weighted average. If all these weights are equal to each other, then we would be computing an unweighted average. Okay. All right, here's an example of maybe like a grade point average computation. Suppose that a person took some classes for a term. They took maybe an algebra class. They took a music class, maybe a history class, and maybe an English class. And maybe they took a basket weaving class, okay? Let's say the credit hours allocated to each class. Algebra is 4, music is 3, history is maybe 4, English is 5, and basket weaving is 1. Let's say that the grade that they've attained in these classes, algebra, let's say they got a 3.5, music 4.0, maybe history. Maybe if you were like me, you got a 2.0. English, if you were me, I didn't get no 4.0. I don't know, maybe a 3.0, let's say. Weaving, basket weaving, let's say you got a 4.0 also in it. Okay. How would we compute the GPA for this term here? Well, we're going to basically multiply the weights by the GPA attained, and then we're going to divide the sum of those products by the sum of all the credit hours. So we would take 4 times 3.5 plus 3 times 4.0. Again, the credit hours are the weights, plus 4 times 2.0, plus 5 times 3.0, plus 1 times 4.0. And we're going to divide this by the sum of the credit hours. So these all add up to 7, 11, 16, 17 credit hours. All right, let's get on our calculator and dial it up, and you have the GPA for that term. This is called a weighted average. And you would have a GPA for that term, which would be approximately about 3.117, but they would probably round it off maybe to the nearest tenth, so maybe like 3.1, okay, GPA for that term. That's called a weighted average. I have a question for you. Which class would we want to try to get the best grade in? Which one has the most weight in shaping our GPA?
English.
English.
English does, because it has the largest credit hour or contact hour weighting to it. Which one could we maybe just kind of skimp by a little bit more so on?
Basket weaving.
Basket weaving, correct? It's only weighted at 1 credit hour. It has the least weight, okay? So there you go, ladies and gentlemen. That's called a weighted average. All right, here's a weighted average or weighted mean computed from a data set here. They have some data values and they have the respective weights. I don't know how they allocated these weights. I don't even know what this data pertains to. That's not important for the computational purposes. The last column is the product of the data value times its weight. Sum up the last column and divide the sum of the last column by the sum of all the weights, and you have the weighted average or the weighted mean, which would be 64. So that's how you compute a weighted average. Were you good on that? Weighted average? Okay. Now, this is very important, ladies and gentlemen. These other attributes are important. I'll let you read through them, but the one that I want you to try to remember is this. The mean or the arithmetic mean or the average of a data set is, okay, highly susceptible to outliers. If your data set has outliers in it, your average or your mean, okay, its value is going to be adversely affected. And it's going to do a very poor job to give you a measure of central tendency. Right? The median. The median is least affected by outliers. Least affected. Right? The mode is interesting. The mode is pretty easy to compute. Another thing, ladies and gentlemen, the mode can be applied to nominal, okay, or categorical data, which means the mode still has meaning for non-numeric data. Whereas the median and the mean have no meaning for, nominal or categorical data. The mid-range is also what? Strongly affected by outliers. So again, the key is if your data set is plagued with outliers, we should be using the median as a measure of central tendency, not the mean or the mid-range. The nice thing about the mean when your data set does not have outliers in it is that it is very sensitive to all your data points in its computation. The median does not take into account the actual value of all your data points in the data set in its determination. So the mean is the most sensitive statistic for a sample. The mid-range is the least sensitive in that it is only computed by using 2 data values. The median is a little bit more sensitive, but kind of lies in between the other two. All right, here are some frequency histograms for some data sets, and we've already indicated that the shapes have meaning. For instance, this first top one up here is like we would say positively skewed, as it tails off more gradually to the right of the highest bar or class as opposed to the left. We say this is skewed to the right or positively skewed. If your data set does possess this positive skewness, then this is how your measures of central tendency would stack up relative to each other. The mode would be represented by the highest bar, if you will. The median is always in between the mode and the mean. So the mean would be shunted further to the right on the horizontal axis. The mode would be the numeric value on the left, and the median would be the numeric value in between the mode and the mean. If your data set is symmetric and bell-shaped, like this middle histogram indicates, it's a well-known fact that your mean, median, and mode are all very close to being equal to each other. They may not be exactly equal to each other, but they're extremely close to being equivalent to each other, all of these statistics, okay? If your data set is negatively or left skewed, then the mean would be the smallest of your three measures of central tendency. The median would be the next greatest measure, and the mode would be the greatest measure of all three statistics. Just remember, the median is always in between the mean and the mode, okay, for skewed data, all right? All right, so that ends that. Okay, we don't have a ton of time left, but I want to go to our textbook again, see if we can do that. Now, we did 2 classworks already. So I'm going to go to section 3.1. Okay. Go down to the homework problems down here, or actually the textbook problems. And let's just see if we can have a little bit of fun here. All right, ladies and gentlemen, problem number 1. They give you a small data set here, and that's the good news. It's manageable. They want us to compute the mean, the median, and the mid-range, and the mode for this data set. So I would like you to compute these measures of central tendency for that data set. I would recommend that we do what to the data? What do you think we should do to the data?
Put it in order.
Yeah, let's just throw it into a list on our calculator and then sort it maybe in ascending order. Okay, go ahead and do that. We'll check these values out, okay? Do problem number 1. This will be called classwork number 3, problem number 1. All right. The mean, what do we get for the mean? Anybody?
I got 104.
All right. I believe they rounded off the nearest tenths, although you did not specify any instructions where to round off. So, I mean, you're not really responsible for that per se, but I rounded off the nearest tenth. But did you get 104 and some change?
Yeah.
For the mean? Okay. Yeah, but hey, don't worry about it. They didn't tell you where to round off. But if they do say round off like to the nearest tenth or the nearest hundredth or 1 or 2 decimal places, then yeah, you want to pay attention to that. But good. All right, pretty simple to get. You just add all your observations together, divide by 14. I believe there's 14 observations. All right, the median. I computed the rank of the median value. 14 plus 1 divided by 2 is the rank is 7.5. So the data point that measures 7.5 in rank would be the median. So I sorted all my data, counted up 7.5 ranks. So rank number 1, 2, 3, 4, 5, 6, 7, 8. So rank 7.5 is between rank 7 and 8, which is going to be the middle value between 102 and 102, which is the average of 102 plus 102, which is 102. That would be your median value, 102. Notice in this case, 102 is actually a data point in our data set. That's not always the case, though. All right. Especially when you have an even number of observations in your data set, your median may or may not actually be a data point in the data set. The mid-range value is nothing more than the average of the minimum value in a data set and the maximum. So 50 plus 160 divided by 2 is 105. Modes. What do we get for the modes? Well, the modes are the most frequently occurring data point or points in the data set. 50 occurs twice. Do you agree? 95 occurs what? Twice. 102 occurs twice. And doesn't 160 occur twice? Is that true? It looks like this data set has 4 modes. So we would say it's multimodal. I've never seen any textbook where it was coined as being quadmodal. We just call this multimodal. Right? Question: are all these measures of central tendency, with the exception of the modes, of course, are the 3 measures of central tendency, the mean, median, and mid-range, are they all comparable in value? Pretty close to each other?
Yeah, that means no outliers, right?
105, 102, 104.1. Yeah, they're all pretty close to each other. And we would expect that to be the case because our data set does not have any outliers in it. It does not appear that this data set has any outliers in it. And we'll show you an exact numerical test you can subject the data point to if we suspect it to be an outlier to determine if it indeed is an outlier. Okay. But does this make sense here? Computing some measures of central tendency of a data set? Pretty simple. All right. All right, just make sure when you go to Alex that you do have your, your calculator handy next to your side to help you out. Ladies and gentlemen, I want to show you another feature on our calculator, the TI-84. We have just enough time here. Let me show you how you can find the descriptive statistics for a data set. Of course, we first of all go to Stat, Edit, and we enter our data into a list. And once your data is in a list, and it doesn't matter if it's sorted or unsorted, you go back to Stat. You go over to your Calculate mode, and you stay on 1var stats. This is short for one variable statistics. Hit Enter. So Stat, Calculate, 1var stats, hit Enter. My data is in list 1. Make sure you got the appropriate list. Leave the frequency list blank. Go down to Calculate, hit Enter, and all of the descriptive statistics for that entire list of data are computed. You got your mean. This is the sum of all those observations. This is the sum of the squared observations. This is your standard deviation of a sample, the standard deviation of a population. We'll indicate why they're a little off. We look at the formulas of variation down the road. 14 observations of the data set. The minimum value of the data set is 50. Q sub 1 is called the first quartile or the 25th percentile of your data set, which is 91. The median is the second quartile, also known as the 50th percentile of your data set, which is 102. And your third quartile, or your 75th percentile, is 120. And your maximum observation in your data set is 160. We call the min the first, the second, third quartile, and the maximum value the 5-number summary of a data set. It's called the 5-number summary of a data set. So the 1var stats function is pretty cool. I mean, it computes a lot of information very quickly, which would take us a ton of time to do manually. Okay. So now you know how to compute variant 1var statistics for a list of data. All right, ladies and gentlemen, that's it. We dealt with measures of central tendency. We did a couple of graphs back in sections 2.1 through 2.4. I did up 2.1 through 2.3. I did update all of the 2.1 through 2.3 homework on Alex. Make sure you get started on that. I believe the homework is due by midnight, September 16th. And after that, there's a 10% penalty. The chapter 3.1 homework I do not have on Alex yet. I will get it up and running as soon as I can. But with that, I will. Oh, wait a minute. Wait a minute. Wasn't there something else? Was there a quiz that had to be opened up?
There's an exam from chapter 1 and 2.
Wait a minute. Let me see. Hold on a second. Let me check the schedule quickly. Yeah, ladies and gentlemen, there is, wow. There's going to be an exam on chapters 1 and 2 material that I will open up on Alex, and it will be due by midnight, September 17th. Okay. And I will get that exam together and get it opened up. I'll try like heck to get that opened up before today is over. Okay. Does that make sense? What's going on? All right. What order do we do things when we do things on Alex? We always do the what first? Homework. Always do the homework first. Then do the quizzes if there are any quizzes. There's no quiz this time. There will be in the future. And then do the exam. So homework, quizzes, exam in that order. Okay. All right, I'll stay on the line. If you have any questions, please let me know. If not, have a great weekend.
Have a good day.
We'll see you.
Have a good day.
All right. See you.
Can we go over the classwork question with the dot plot?
Yeah, the dot plot. This is the dot plot. Basically, hold on a second here.